Swayam Prabha. Digital India. Educated India.
Welcome to the class of Intelligent Product Design. We are in the process of material selection. In the last class, I have just introduced you to the process of material selection, the nitty-gritties, and in this class, I will introduce a little more complexities in the process through some case studies. The first case study is material selection for simple cantilever design. Okay. You can imagine a cantilever to be the branch of a tree like this, which is hanging some load. You can put some load from that branch, and then this essentially behaves like a cantilever beam. Now, you look around, you would see there are many examples of such cantilevers all over around us in the form of products. For example, if you consider the aircraft wings, then this also in a way it behaves, we would say structurally it is analogous to this particular tree branch, and it also behaves like a simple cantilever beam in its elementary form. Of course, there are many complexities there. For example, you would see there is a main part, then there are spars there which is used to maintain the shape of the aerofoil, and also according to that kind of a shape you will get a variation of load. But in the core these two resembles the same, that they are essentially simple cantilever beams to begin with. Now, if it is a cantilever beam, now naturally in case of a aircraft wing you would like it to be as light as possible, because it has to fly in the air. So, to have something which is light, yet it has to be steep, because if it is not steep, then this aircraft wing will bend so much that will create further problem in terms of aerodynamic interactions and all other problems related to the entire system. So, we would like it to be always light and steep and also light and strong. Now, let us look into it that for a cantilever beam, if it is light and steep, then how would it be the problem statement for us? So, if you look at the problem statement, we have to select a cost effective material, keeping in mind high stiffness, but lightweight. And I will do this problem in different ways, like suppose first we consider this entire problem for a circular beam cross section. Of course, an aircraft wing is neither rectangular nor entirely circular, it is something like a aerofoil shape, but let us just try to do it for a circular beam cross section. And the constraint is maximum deflection and beam length. You cannot have indefinitely large beam length, and the deflection also, as I told you, because of aerodynamic interactions, you cannot have too much of deflection in the system. So, what is the free variable in this case? Of course, it is the cross sectional area that we will keep as the free variable. So, let us try to do some sample calculations. Okay. So, here we have a cantilever beam. Okay. Let us say I put this one like this, and if I take a cross section of it A, then it would be something like this, a kind of a circular cross section. I am just giving you an approximate idea of it. Okay. So, suppose if it has a radius r, then I can write this area as pi r square, that we know. And also suppose this is a cantilever beam and the load is coming at the tip. Of course, the actual truly speaking it will never be at the tip, but that is the worst condition. So, there is a force F, and the length is specified already. Okay. Area is the free constant, but not the length. So, what will be the end deflection here? That is also specified, the maximum deflection that it can have, delta. Generally, delta for such simple case will be f L cube over 3 E I, where I is the modulus of elasticity of the system. So, what is the modulus of elasticity I of the circular beam? Well, I is approximately pi r to the power 4 by 4, that is the I. And what is the mass of this cantilever beam? Well, mass of this cantilever beam, I can write it as the cross sectional area times length times the density of the material. And I told you that this area is a free variable. Okay. Can we get this area expression from this expression of delta, the deflection? We can actually. First of all, in 2 steps we have to do it. We have to first of all write I in terms of all the other specified variables, that is I would become f L cube by 3 E delta. Force is specified, deflection is specified, length is specified, E is so far the material property here, but then I is what? Pi r to the power 4 over 4, that is f L cube over 3 E delta, and that means r to the power 4 is actually 4 f L cube over 3 pi E delta, and that means r square, which is what will be important. So, this will be square root of 4 f L cube over 3 pi E delta. So, pi r square, that is the area, is simply pi times this, and that is nothing but the area here. Okay. So, now let us just write it here, pi r square equals to area equals to this. Okay. Now, you have this as the area, and then I can now suitably replace it here, that the mass will be now as pi square root of 4 f L cube over 3 pi E delta, right, times L times rho. So, I can also now separate all the variables, keeping the functional part together along with all the constants. So, one way to do it is that take even the pi inside. So, you get 4 pi square f divided by, you have 3 pi E, okay, and I am keeping this L cube part as separate. So, which means you can have that geometry part here as square root of L cube and L together. So, it will be L to the power 5, and then we have the material part which we are looking for, and you can write it as something like rho square over E. And in fact, you can simplify these from these, the material property index M as something like E over square root of E over rho. Okay. So, that becomes our material property index corresponding to the light cantilever beam, which means very simply that if I want to reduce the mass of my aircraft wing, then from the material point of view, I have to reduce square root of rho square over E, which is equivalent to the increase of, look, this is capital M, okay, do not confuse it with the small m, the increase of the material property index, and such that square root of E over rho is actually maximized. So, keeping this point in mind now we know that the performance index is square root of E by rho. Then let us start to take some materials like steel, like wood, like concrete, aluminum, CFRP, we know they are modulus of elasticities. In fact, CFRP we have taken in the lower side, CFRP can be even more than this, and steel is generally 210, but for the sake of calculations we have kept it simply as 200. Our point here is to actually get a qualitative idea. Then the density is also we know for each one of them, and then square root of E by rho if we try to figure it out. The interesting thing is that for the CFRP we get the square root of E by rho as something like 8.84, which is the best. CFRP is the best material, and no wonder that is why most of the aircraft's wings are actually made of composites, because cost is slightly, I will tell you later on, that slightly less sensitive factor in terms of building an aircraft. Okay. When you are developing a bicycle, you may be more cost sensitive than when developing an aircraft. Interestingly, what is the next best choice? Next best choice is wood, and you see, no wonder that the Wright brothers had actually rightly chosen wood for their initial models, and even today most of the aircraft models are actually made of balsa wood. So, wood comes out to be the next best, and then of course, aluminum comes into picture, which is better than steel. Even steel is worse than concrete in that sense. So, the cost wise also, if I leave wood, then aluminum alloy is expensive, but I told you that we are not that cost sensitive here. So, this is something that we can also see graphically from here, that square root of E by rho ratio will be some such region. Okay, this is the slope of square root of E by rho, and then this from this such region whatever will be coming towards the upper side of this slope will be of our interest, and of course, we will look for materials which will give us high E, but as low rho as possible. That is why some of the composites here are better than some of the metals, because they give you lesser E in that sense, lesser density in that sense, so that you get a higher square root over E by rho. I will now come to another interesting case study, just extending this concept. Okay. So, design of a scanning probe microscope. Okay. Now, scanning probe microscope is something that is used for AFM and many high precision scanning of the surface of a material, and there the probe, which is like exactly like this, but in a very small scale, actually touches the material and gets the repulsive force from the atoms itself. It is so very sensitive. So, for the tip of the scanning probe microscope, let us say we are trying to check that what will be the optimal design. Here, instead of light and steep, one of the criteria that we will have is that because it works like a mechanical resonator, so we would like to increase that resonating frequency of the system. So, SPMs, the scanning probe microscopes, are generally designed with high resonating frequency. Why is it so? Well, it is because if the resonance of the tip interferes with the force that it is getting from the atom, then you will get an inaccurate measurement of the atomic force. So, that is why they try to keep it away. Now, how do I do it? In order to do it, just you keep in mind that there is a piezo sitting here. Okay. What is the purpose of that piezo? Whatever is these deformations or movement happening here, the piezo converts it in terms of electrical voltage, which is what we see in terms of the scanning image. So, such piezoelectric material, I have talked in details about it in my course on smart materials, but here just to give you an idea that these things have two effects. One is called a direct effect, another is called a converse effect. So, in the case of a direct effect, what you are getting is that if you are applying stress, which is what is happening in this case, you are going to get electric potential. That means a change in terms of the charge. Okay. So, that way you can use it as a sensor, and in the converse effect it is the other way around, that is, if you give an electric field, you will be getting deformation in the system, which we will not utilize in this case, but we will utilize the direct effect of the piezoelectric material. Now, in this direct effect, the piezoelectric material can be used as a bimorph, which can sense the change of the deformation in the system, and we can get it as a D31 sensor. As I told you, every piezoelectric material can be used as a sensor as well as an actuator, but in this case we are using it as a sensor to sense the change of force and then get it in terms of the voltage. So, that means, if this material, the piezoelectric material, as a bimorph that is attached with another passive material vibrate this way or that way, that would create in terms of time versus voltage plot this vibration, this deflection that is happening here is going to create a voltage, okay, and that is the voltage that can be used for sensing. Now, let us come back to the probe now. Now, the probe has some natural frequencies, okay, and which can be described with the help of this equation, which is a form of square root of k by m and simply in terms of rad per second. So, that is the question now is that what is the k? Well, for a cantilever beam, the k can be assumed against the bending, and then it becomes 3 I over L cube. So, if that is the k and I also is known to us, then we can go one step further. We can actually write the expression of f in terms of not I, but in terms of the geometrical parameter, because we have to finally do this exercise with respect to one of the free variables of the system. Now, then what is the kinetic energy of this system T? T equals to m, that mass, okay, per unit length, and then it is that del y dou y x dou t. What is that? That is nothing but the velocity. Okay. So, it is something like a mv square integrated over the entire length. Now, what is y x? Well, y x can be approximated. Okay. This is a Rayleigh approximation for a cantilever beam, that y x is, if the end deflection is y max, remember that the deflection is varying at each and every point. So, it is a function of x, and you can express it as a function of x this way, and you can put these things so that you get an idea about the effective kinetic energy, and from there you can evaluate the mass, which will come out to be about 9 by 20 m. So, this is a very accurate analysis, and that will give us the frequency. Finally, once I put all the variables, you will get it frequency as a function of square root of E by rho. The difference with respect to the last case is, in the last case the expression was m was square root of E by rho, right. That was the material property index for light stiff structure. But against this resonating system, okay, high resonance F, you need to maximize not square root of E by rho, but here the m that you need is full square root of E by rho. This matters. Okay. That is why I thought of putting this in your mind. Now, you try to use all these materials like aluminum, brass, steel, tungsten, okay, and there is, okay, each one of them in terms of 10 to the power 10 Newton per square meter, and you will get E by rho. So, you can easily square root of E by rho, but this E by rho is telling you that so far out of all this material, 2 probes could be good. One is if you go for aluminum or if you go for steel. However, in that small scale, if I have to develop something, I have a better material available with me. This material is known as silicon nitride, and silicon nitride has a modulus of elasticity of 24.1, that is 241 gigapascal. 24.1 into 10 to the power 10 is equivalent to 241 gigapascal, more than steel. Not only more than steel, but steel's density is 7,800 kg per meter cube, and this is 3,200 kg per meter cube. So, that means the E by rho here is 7.5, which is the highest, and no wonder that is why silicon nitride is used as a probe for the SPM whenever you are actually maximizing the resonating frequency of the system. I have not touched the issue of piezoelectric material. At a later stage, I will show you how to do that. Now, this entire process, thanks to Ashby, you can actually use Ashby's material property chart beautifully. Okay, I would recommend you to read this book if you can get it, a copy of it, and it has shown fantastic way that how different materials are placed. Like in this case, it is E by rho that we are looking at, and one important thing here, you also would see that the slopes are given here, like E by rho slope is this one, whereas square root of E to the power half over rho slope is this one. And of course, it is not shown here full square root of E by rho, but you can similarly draw these slopes. And what you need to do is that based on your requirement, you need to sort of translate this. Okay? That means, based on a cutoff level, you translate this curve and you draw this, these parallel lines. Okay? Each parallel line is showing the same property, but starting with a higher initial value, so that the cutoff level is already known to you. So, suppose if my cutoff level in this case is 1 GPa, that in no way I can have a probe whose modulus of elasticity is less than 1 GPa. Then this is the line that we have to see, and then in this line I have to see what are the material that is coming up above it, like CFRP, like Si3N4, okay, some titanium alloys, though they are mostly here. So, it would not come Al2O3 ceramics mostly. Okay. So, that is the way you can use Ashby's chart, and it is not only for modulus of elasticity, but also for the strength density. You can use this chart if you want to maximize the strength, once again corresponding to different type of slopes. You can draw that, and then you can actually utilize it. Now, let us talk about a few more complex cases. Okay? Like we can have multiple constraints. Okay? So, if we have multiple constraints, what do we do? Well, one way to do is that we can actually choose material property index corresponding to each of these constraints and sequentially apply these indices, or you can use some weight factors or fuzzy logic, or you can go for a systematic selection. And finally, you can have not necessarily only one objective of light system, but you can have a light mass along with a low cost. So, two objectives. So, that also we will see very quickly. Well, let us take first this case study from Ashby, that is on a connecting rod design of a bicycle. Now, what is the connecting rod? Connecting rod is this system which actually transforms the vertical motion that you put on the pedal into the rotational motion of the system, because for stability the bicycle wheels has to continuously rotate. So, that rotational torque you have to supply, and the connecting rod exactly does that. Now, while doing it, you have to keep in your mind that there are two things that a connecting rod has to have. One is that it should not buckle. Okay. Another is because if it is too long, there is a chance of buckling, and another is that because there is a dynamic loading, so it should not fatigue. So, we are going to choose the lightest material which will neither buckle nor fatigue. That is a case of multiple constraints. Let us look into it then. Okay. So, this is the connecting rod. We have to minimize the mass of it, light, must not fail by buckling under given force, must not fail by fatigue under given force. Okay. And then in this case, then what are the two cases that is giving us? One is the fatigue is telling that the stress that is coming into the system has to be less than the endurance strength. So, this is the endurance strength. So, if it is less than the endurance strength, then you know that the material can sustain almost infinite number of cycles. Okay. So, then I know that F over A is sigma E. In other words, from this expression I know that area is nothing but F over sigma E, and then I can replace it in this equation. So, then the mass will be what? Mass will be K F over sigma E L rho. Let us write this sigma E here, it is a subscript. Okay. So, that means I can again write it in a variable separation form and write this rho over sigma E separately. So, that is what is my first material property, and in order to reduce the mass, I have to minimize rho over sigma E, or in other words, if m is sigma E over rho, which is more conventional, then I have to maximize this m1, first property. Okay. Second one, you can do the same way I have done earlier for that circular beam. Okay. Only a small change that you can do is that the I here need not be exactly circular. Okay. So, the I generally we take it what as pi r to the power 4 by 4, right. So, instead of that, we will be taking it approximately as, let us say that we will keep it as a factor alpha and put it as pi square by 12 r to the power 4. Okay. So, if I do this, alpha is a geometry factor of the rod, and then substitute it in this equation, carry out this exactly what we have done earlier, you will come up with rho over square root over E, which will be, that means the m2 in this case is E to the power half over rho, which you need to maximize. So, in one case sigma E over rho, in another case E to the power half over rho. How do I proceed? Well, I can do it sequentially. I can use this endurance limit graph and do this, and similarly I can do it over the square root of E by rho. Both of them, if I do, interestingly, the first case for fatigue will tell me CFRP is the best material, for buckling also CFRP, but I told you a bicycle is expensive, you cannot use CFRP. What is my second choice? First case is telling for fatigue, go for titanium, whereas second case is telling go for magnesium, of course some alloy of magnesium or some alloy of titanium. So, there is a conflict, which one to choose. So, this method is not very good. Okay, one way to do is that you take a weight factor. You say that I will take W1 of this and W2 of that, but however, many times we do not know what will be the weight factor. So, sometimes we apply a fuzzy logic, that means we know that the properties are not exactly like this. So, this is what is called crisp probability, but it has an area like this. So, that overlaps. So, that is one way of doing. However, a better way of doing this problem is through systematic selection. So, what we do here is we exactly find out the mass of the two things, and looking at the factor that both the cases, anything else but the length appears in one case as L square, in another case as L. So, that means mass is linearly varying in one case, that is the case where the fatigue is concerned, and the mass is varying like a curve, non-linear way in the second case. So, and there is a cutting point here. So, that means up till this point it is the length that predominates. Okay. So, if the length is less, then fatigue is more important, and beyond this critical length LCR, buckling becomes important in the system. Accordingly, I can apply the material property index. Exactly the same thing has been done here. With all the materials, we have obtained the M1 and M2s corresponding to each of the materials for each one of these two cases of fatigue and buckling, and then whatever is going to be the maximum between the two, we put it. Okay. This is also known as minimax principle. So, corresponding to both the cases you do it, and then figure it out that which one is going to be the lowest solution. One is CFRP, another is ALSIC, the Duralcan type of a thing, aluminum silicon carbide. So, that we can do. Another way we can do the same problem is that there is a conflicting objective. So, you can use a Pareto optimality, and you can get a Pareto optimal front. So, you have mass of M2, mass of M1, and get the Pareto front and figure out that at what are these choices at the Pareto front, like this at this point comes out to be the best solution of the problem. Now, if you have multiple constraints, so choose best materials based on M1, then M2, and find the common members, that is one way, or take m's for each material and normalize by maximum value and then figure out the final value. That is, you consider it to be one single objective situation. Now, sometimes we can keep it as a compound objective problem, and what we look for is something called a value function or a compound objective problem. What we require in a value function is that we need to know the exchange constants, right. That means, if I have two value functions or a value function with two properties, then what is dou v dou v, and that is going to give me the exchange constant. So, then I can create my value function as exchange constant corresponding to one property plus exchange constant corresponding to another property. As they say that in every trade off there is something that you are paying, and that paying is in terms of the cost. Okay. So, the cost itself we consider it as minus 1, and then so we use this for every objective we use this concept of the exchange constant E and keeping the cost as minus 1, and then you can do this problem graphically, and you can see that in case of a bicycle, the mass of the bicycle, if it is of not your concern, then the exchange constant becomes something which is pretty low at a higher value of mass, which means if you are going for a heavy bicycle, okay, and not in a high end, in a low end, then you do not have to think much about the lightness of it, because the exchange constant is only $20 per kg. Whereas, if you are going for the high end, okay, then the slope is much sharp. So, every single gram there, okay, is very, very important in terms of the exchange constant. So, you can see that titanium becomes an important choice here, and whereas here you can see the plain steel becomes an important choice, because this side of the Pareto front is less mass sensitive, but this side is very high mass sensitive. So, that is the way, by the use of value function, if you know the exchange constants, okay, you need a bit of experience to do it, you should be able to actually choose the material corresponding to compound objectives. So, and not just only one objective, but there are multiple objectives. If there are more than one, more than two, let us say 3, 4, 5, then this curve will become multidimensional in nature. That is the way we can solve the problem. Thank you.